So we're looking at what could cause a derivative of a function to fail to exist. So we're going to start by looking at the function absolute value of x, which we have graphed here. And if you notice, there is this corner that occurs at x equals 0. And the derivative of this function fails to exist at x equals 0. And in general, we would say the derivative of any function that exhibits a sharp corner like this would fail to have a derivative at that location. Now let's think about the interpretation of the derivative as slope of the tangent line. If I look to the right of x equals 0 and I think about the idea slope of the tangent line, or slope of rate of change, well, to the right, that rate of change is 1 over 1, or just 1. To the left, I see that the slope, or the rate of change, is negative 1. So that's why we have a difficulty here. Is on the right-hand side of 0, that idea of slope or rate of change is 1. On the left-hand side, that slope or rate of change is negative 1. So we cannot resolve a jump from negative 1 on the left to positive 1 on the right. So we say that the derivative does not exist at x equals 0 because there is a sharp corner that occurs at that point. Now, a second way a derivative could fail to exist is in the presence of what is known as a cusp. So we have the function here at 3 times x to the 2/3 power, and this is its graph. And if you look how it pinches down here and then goes up like this, this is different than a sharp point or corner. This is referred to as a cusp where this pinching occurs. So in the instance of this function, if we think about slopes of tangent lines and rates of change, the rate of change, notice that this function is becoming nearly vertical. And so the slopes of the tangent lines are actually approaching either positive or negative infinity, depending on which side you're looking at, the left side of 0 or the right side of x equals 0. So in the presence of this cusp, or this pinching where the slopes of the tangent lines become nearly infinite, we say that the derivative would fail to exist. Now we look at a third way that the derivative of a function could fail to exist. And here we have a function where at x equals 1, so right in here, we have a vertical tangent line. Okay. Vertical tangent line, in general, we say slopes of vertical lines do not exist. And since we use as one of our interpretations for derivative the slope of the tangent line, we would have to be consistent, say that that does not exist because the slope of the vertical line does not exist. So in any instances where the function might have a vertical tangent line, then the function, we would say that the derivative fails to exist due to this vertical tangent line at x equals 1. We now look at a fourth way a function can fail to be differentiable or have a derivative. And this is due to functions having a discontinuity. This graph here is part of what's known as the greatest integer function. You really don't need to know what that function is, but just let's look at its graph. And if you notice, these are horizontal lines that jump at each of the integer values on the x-axis. So the problem with a function like this having a derivative is that at each of these jump points, the function is not locally linear. That means I can represent in a close neighborhood of x equals 1 this function with a line. Well, at x equals 1, I have no possible way to represent this with a line, because to the left of x equals 1, I would have to use the horizontal line y equals 0, and to the right of x equals 1, I'd have to use the horizontal line y equals 1. So at the point x equals 1, there is not a single line that could be used to represent this function. That is, it is not locally linear. It cannot be represented by a tangent line. Therefore, the derivative fails to exist.